So today I want to start up the next section, which is conservation laws. And I want to focus on a couple of things. One is I want to introduce the idea of classical symmetries. I'll give some examples of classical symmetries. I'll then talk about what makes a symmetry quantum symmetry, so it's between a quantum system. And then we'll just make some notes about what happens when you have a classical symmetry that does not assist to a quantum system. And I'll introduce the idea of anomalies. I won't spend too much time now, but I just want to make a note of what an anomaly is, and then we'll return back to this a little later when we complete the conformal order identities of the associated conformal anomalies. So, by way of kind of motivation of this section, I'll tell you why we're interested in this section. You know, one of the deepest, most profound statements in all of physics is goes by the name of Newton's theorem. Newton's theorem has an interesting history. Back in 1916, when Einstein wrote down his general theory of relativity, it wasn't, of course, universally accepted, and there were a lot of things about this theory that were strange and unfamiliar, and people were trying to understand it. One of those people had more or less understood the mathematical structure of relativity about a year before Einstein did. This was David Hilbert. One of the things that Hilbert knew immediately was that the concept of energy in general relativity was not as well defined as it was Newtonian theory. And so he hired a young mathematician from Minnesota to come to Göttingen and try to understand when energy was conserved in general relativity. And in studying this problem, Newton not only managed to understand the problem in general relativity, but he gave a general statement for theorem that said when you should have conserved quantities, not just energy, but conserved quantities in general. And Newton's theorem basically tells us that for every continuous global symmetry that we have in a system, there is some conserved quantity. There's a conservation law. Every continuous global symmetry. All of these words are important. And what I want to do today is unpack these words before we actually get to a proof of Newton's theorem. And we're going to give a couple of different proofs of Newton's theorem. We're going to give 3 proofs in total, 2 of which will be classical. One will be the classical proof. And the other one will be a proof that is closer to the quantum proof. And then we'll give a proof of quantum statement. That's going to take a little bit of different technology than you're used to, but I have pointed you to my notes and functional methods. And I'd like you to go over that preferably before the end of Friday. So just familiarize yourself with the idea of a functional integral and as it applies to quantum mechanics. We won't need to actually calculate it, but I need you to know that if you want to calculate averages of quantities, quantum systems, these are called expectation values. If you want to calculate expectation values of certain operators, then this is how you calculate it using functional methods. There are, of course, operator methods for this as well, but we won't be using that because the functional methods are so much more powerful. So again, Newton's theorem tells us that for every continuous global symmetry, there is a conservation law. What we want to do is try to make this statement mathematically precise. I need to expand on what all of these words mean, starting with what exactly is a symmetry. Okay. So suppose I have some. Can I borrow your? Suppose I have some unmarked pencil, right? There's nothing that distinguishes one side of this from the other. You kind of pretend that there's no outside, right? If I hold this down, in fact, let me take this one. If I hold this down, I want to drop it, and I don't want to drop it. So if I hold this down and I rotate this pencil, and ask you to close your eyes, and I rotate this pencil about its vertical axis by some amount. Okay, if it's an unmarked pencil, then when I say open your eyes again, you can't tell that I've made a change to the system. Okay. Technically, what we say is that rotations are a symmetry of the pencil. Okay. So again, intuitively, the way we understand symmetry is you make a change to a particular system, and if you can't tell, system can't tell that a change has been made, then we say that it is asymmetry. But this is just intuitive. These are just nice words, and I would like to make this more precise. So, in building up to making this more precise, let's talk about a slightly deeper symmetries and then rotations of the pencil. Let's talk about Lorentz symmetry. Now, all of you at this stage have learned about special relativity. Right? Special relativity, one of the key features of special relativity is that the laws of physics do not depend on which inertial frame you are. Right? If I'm standing still and you're moving past at a constant speed or constant velocity, then you can't, there's no measurement that we can make that will allow us to distinguish between who's standing still and who's moving. We're both in inertial reference frames. Okay? So there are transformations called Lorentz transformations that allow us to go between inertial reference frames. The key words here are inertial. Okay? So there are the fact that the laws of nature are Lorentz invariant mean that we can't do any experiment to determine the constant, possibly non-zero velocity of your inertial reference. Right. That's the essence of special relativity. So the laws of nature are Lorentz invariant. Implies that we cannot determine the constant of the non-zero velocity of any inertial by any meaningful experiments. Now I have to tell you what a meaningful experiment is. One meaningful experiment is studying the dynamics of charged particles. Right? So if I want to be excited about this, I should add to this. We cannot determine the constant velocity of any inertial reference frame by studying the dynamics of a charged particle. This is because any charged particle, dynamics of any charged particle will always agree with Maxwell's equations, Maxwell dynamics in any inertial frame. In fact, this is so much so that we can take as a definition of what an inertial reference frame is, as one in which the dynamics of the charged particle is perfectly described by Maxwell. Right? Otherwise, it's very difficult to agree on what constitutes an inertial reference frame. Right? But the fact that any charged particle will always obey Maxwell's laws, Maxwell's equations, in an inertial reference frame, we can use as a definition of an inertial reference frame. So, inertial reference frame is one in which a charged particle is perfectly described by Maxwell's equations. In fact, if you look at the history of the development of special relativity, it was not the Michelson-Morley experiment that led Einstein to the discovery of special relativity. It was the fact that Maxwell's equations work so well in different inertial reference frames. Okay, and trying to understand the consistency of Maxwell's equations, particles known on accurate equations, is what leads ultimately to special relativity. Another way of saying exactly that, namely that the system is Lorentz invariant, means that we can't determine which inertial reference frame we are in, is to say that Lorentz transformations, the transformations that take between these inertial reference frames, map solutions of the Maxwell equations into solutions of the Maxwell equations. Okay, what I'm trying to do here is take a vague statement like what is a symmetry and give this intuitive idea first, and now we're refining the intuitive idea. Right? First refinement comes with looking at a particular symmetry. Right? It's a little deeper than this rotational symmetry story, but it's allowed us to formulate things in terms of equations. From there, we're refining it a little bit further, and what property of the equations in particular, right? The fact that those equations are invariant and Lorentz transform. So, Lorentz transformations solutions of Maxwell equations into solutions of Maxwell equations. That's a key. Okay, these are maps on the solution surface of the Maxwell equations. So that seems like, some pedantic rewording or whatever on that before, but actually it's not deeper than that, because it gives us a good foundation to build more precise definition or what classical sort of things. Okay. So one thing we know is that any field, right, both on fermion, gauge field, four vectors, electromagnetism, any field that satisfies the classical equation of motion must minimize the classical action. Right? So I have a Lagrangian, integrate that over time, I get an action. The action encodes the equations of motion to the Euler-Lagrange equations. Right? And I know that any solution that satisfies the equations of motion must minimize that action. Okay. So since any solution, okay. Building on this last statement, any solution of the classical equations of motion must minimize the classical action in the sense that delta s by delta phi equals 0. This gives us a good working definition of what a classical solution is. So a classical symmetry, for our purposes, is some transformation of dynamical variables in the theory, whatever this is. I'm using phi as a placeholder for anything you want. Bosons, fermions, gravity, it doesn't really matter, right? So a classical symmetry is some transformation of the dynamical variables in classical theory that leaves the classical action invariant. Okay. So a classical symmetry is a transformation of change dynamical variables theory that leaves the action invariant. Okay. So now we have a working definition of what a classical symmetry is as a mathematical one. And it's a good definition of classical symmetry, but as we will see just now, it's not enough for a quantum theory. How we modify it is going to be crucial for building what we want to do for our quantum theories. But let me give you some examples to illustrate this before we go on. And I want to give an example in a concrete setting. So I'm going to write down an action for a particular theory, and then I'm going to explore some of the invariances of this particular action. Then what we're going to do is try and give a more general statement. Then we'll go on to the quantum level. Okay, so consider the following. Consider the following action for a complex scalar field. So S, the action is going to be a function of the scalar and its conjugate, which I'm going to think of as independent variables. Another way to think of this is that a complex scalar is made up of two parts, the real and imaginary part. So there's really two scalars involved in the story. I think of those two things as independent. So if I combine them into phi and phi conjugate, then I think of these things as independent. What this means is that when I do variation of this action, when I take a functional derivative of the action to minimize it, I have to take derivatives with respect to phi and phi conjugate independently. That gives me two different orthogonal equations which need to be solved simultaneously. So this is going to be in 4 dimensions. I'm going to use the mostly minus thing metric. So d mu phi, d mu phi star minus m squared phi star minus some coupling g of phi star squared. So this is a massive complex scalar with a quartic interactive. Okay. This is a quartic interactive. This is last term. Last term is always the quadratic term in the action. This is what's called a kinetic term. This term that contains derivatives. If you're used to thinking of the Lagrange density as a difference between a kinetic energy and the potential energy, this is not quite that. The kinetic energy is the thing that just involves time derivatives. This actually contains some potential as well. But conventionally, it's called kinetic term. It's term involved derivatives. Okay. So, the first point I want to make here is that if I make a change in variables of phi and phi conjugate as follows. I'm going to send phi x to minus phi of x, and at the same time, phi star to minus phi star. Then d mu phi, d mu phi star goes to d mu minus phi, d mu minus phi star, which is the same as d mu phi star. So the kinetic term is invariant, and obviously the quadratic and quartic terms are invariant as well. In other words, the action is invariant under this change of variables. Okay. When we say that the action 1 is invariant, I'm sorry. A global internal Z2. So and these words mean the following. So global means that the x's here are the same x. So this change of variables that I'm making at the same point in the space drive. Okay. So, same everywhere. Space-time. Internal means that this transformation acts only on the fields themselves. And not on the x's. Okay. And Z2 is the discrete group 1 to -1. Okay. So this is the set of two elements. It's not the only symmetry that this action has. In particular, notice that if I make the following change of variables, so the action say it like this. Action one is also invariant under the following constraint. If I said phi of x to e to the pi alpha phi of x and phi star to e to the minus pi alpha, same alpha phi star. Right, and I'm telling you this as separate statements because I'm thinking of phi and phi star as separate independent things. Then under this transformation, clearly S of phi star goes to S of phi star as long as alpha is constant, right? The quadratic terms and consequently the quartic terms are obviously independent again because phi star conjugate pairs. There's an e to the I alpha and e to the minus I alpha. And the derivative terms don't act on the alpha as long as alpha is a constant, right? So the derivative terms are also invariant. So the kinetic term as well as the interaction terms are invariant. So the main point here is that this guy alpha is and we say here that the action is invariant under global internal U1 symmetry. Global and internal mean the same thing as they just did. U1 here is the set of rotations of the origin on the plane. Alpha. This is the set of all objects like e to the I alpha with alpha between 0 and 3.5. Okay. These are just rotations in the plane. Instead of all such rotations in the plane, form the unitary group U1. Think of it as a set of unitary 1 by 1 names. So one immediate question you could think about asking at this point is, what happens if alpha is not constant? And in particular, if alpha depends on where in space-time you make this transformation, right? So what I've done here is a phase rotation. Okay, I've given these fields phi and phi star some additional phase. Right? In this case, where I'm talking about a global internal U1 symmetry, the phase is constant. Okay. Now I ask, what happens if this phase and what happens if this phase change we make depends on where in space-time we make it. Okay. Well, in this case, clearly the quadratic terms and consequently the quatic term will be invariant, no problem there. However, the kinetic term now, d mu phi goes to d mu e to the I alpha function of x phi goes to x. Okay. So here I'll get a term that looks like d mu phi times e to the I alpha of x. That is going to cancel off with the phi star piece. But in addition, I get a term that looks like pi d mu alpha of x, that's phi of x, which is not going to cancel. Right? So in this case, the action is not invariant under local U1 transformation. Yeah. Yes. So this will mean that the action 1 will not be invariant under local U1 transformations. Because in addition to this piece, I will have maybe additional pieces here, as well as the mixing that come from the other side. Okay. This observation, which looks rather innocuous at this point, lies at the heart of gauge theory. It's the fact that the action is not invariant under these local U1 transformations, as well as what it takes to make the action invariant, force the action to be invariant, that gives rise to the idea of gauge theories. And given how many all of the fundamental interactions that we know in nature are gauge theory, this is an incredibly important part. Okay. we will return to in due course. Okay, so this is just some observations about tactical solutions. We're going to make a few more just now, but first I want to give you some idea of what happens when you quantize it. Okay, so again, our statement here with classical symmetry is some transformation dynamic variables of theory and indeed the action variables. Okay, and that's because the chief thing that we work with in classical field theories are the equations of motion. Right. So I give you the action, vary the action, write down the Euler-Lagrange equations, one differential equations. You solve those differential equations with some boundary data, and that determines all of the dynamics of the theory. Right. So if you're a classical field theorist, that's all you care about is the dynamics that arise from the equations of motion. If you're a quantum field theorist, then the dynamics that arise from the equations of motion kind of meaningless. That's because you can't define unique trajectories in phase space for a quantum system. Because in phase space has to obey the Heisenberg uncertainty principle. So individual paths in phase space, again, you wouldn't care about as classical field theorists, don't make any sense anymore. They're fuzzy, right? Because the quantum phase space is inherently noisy. So what do you care about? Well, what you care about if you're a quantum theorist are probabilities of events happening. But the probabilities themselves are derivative objects. I get them from something. And the basic something that I get them from are correlation functions. So if you're a quantum field theorist, then what you really care about are correlation functions. So in a quantum theory, field theory, the basic quantity of interest from which all our observables are computed are correlation functions. So suppose I have some quantum field theory and I'll label the field of this quantum field theory generically by phi. Okay. Then the basic quantities of interest is correlation function. Correlation. So for some generic set of fields in theory, the endpoint correlation function is the object that I get when I take phi x1, phi x2, through to phi n. So this is a product of n fields phi evaluated at different points. Points become coincident, we get a little messy and get to treat those with some care, which will come shortly. But I take the product of these guys, and then I take an average. So the angular brackets are all these variables right now, mean average as you're familiar with them from first year already. Except how you calculate them is involved. So in first year, if I ask you to calculate the average of a function f of x, say, over the interval from a to b, then the average was 1 over the size of the interval times the integral from a to b of f of x. Yes, right? So let's see what key ingredients in the story are. Key ingredients in the story are this thing here. It kind of tells you the size of the interval that you're averaging over. Right? If I wanted to go to higher dimensions than just one dimension, I would call this the volume. So I got 1 over the volume of the interval that I'm integrating over with. And then this is a stupid notation. It's basically the better notation. you integrate over the spatial interval from A to B. You integrate the thing that you're trying to average with respect to some measure. That's it. I need a measure. I need to do an integral over some interval, and I need to normalize by the volume of that interval. So we're doing exactly the same thing here. The only difference is what kind of integral I'm doing. So the normalization function, something that's important, the volume space that we're integrating, is denoted by one of the z. Technically, z is the partition function of the system, but don't worry about that. Just think of it as a non-negation. Integral. Now I do the integral over all of these dynamical variables phi here. Again, this is defined precisely in my notes. But if you go take a look at it, doesn't matter. We're mimicking what we did here. And then I insert all of the things that I'm trying to average over, and this function f into this. And then I insert the last piece of the measure. Okay, in this story, the measure of the integral, the weighting in this integral is the exponential of the classical action. So this is the weighting in this integral that allows me that I can absorb into the overall integral measure. This quantity here is the integral measure. This is the normalization. And these are what we're going to call field insertions. And these angular brackets here define via that integral, by what's on the right hand side here, a quantum average, if you want. Okay, so we're not going to cover this here, but in quantum systems, there are other ways we can average as well. So, for example, in various systems that people are interested in these days, in addition to the fields, there are some impurities. These impurities are very common in finance systems, for example. And in order to keep the impurities, typically inserted randomly into the theory, you have to do a disorder averaging. Right, so there are different types of quantum averaging you can do. I will mean the quantum averaging over the fields like this. And this whole quantity on the right hand side here is called the path interval. Okay. So that's the thing that you want to study in a quantum field theory. Right? These are the objects of interest in the quantum field theory. And in the quantum field theory, not only do we need the action to be invariant under this transformation, I also need the measure to be invariant. Right? So that's the difference between a classical theory and a quantum theory. The classical theory, I only need the action to be invariant because I only care about the equation. If I want to calculate correlation coefficients, then I better be damn sure that this whole integral is invariant. The whole integral is invariant not only if this weighting is invariant, I don't really care what goes in here, but not only if this weighting is invariant, but also the measure of the integral must be invariant. So this gives us a definition of what a quantum symmetry is. So a quantum symmetry is a transformation of the dynamical variable theory that leaves both the action and the path integral measure. a quantum really is a transformation of the number of variables that these both graphical action and the path integral measure variance. So you could ask, well, okay, what if the action invariant, but not path integral measure? Well, if we keep in mind that the action that we're talking about is the classical action, then if the classical action is invariant, that tells me that the corresponding classical theory has some classical theory. But if the path integral measure in addition is not invariant, then that classical symmetry, once I quantize the theory, is broken. Okay? Any classical symmetry that is broken at the quantum level is called an anomaly. So now we understand what an anomaly is. If I have a symmetry in which the classical action is invariant, but not the path integral measure, then I have an anomaly. So any classical symmetry that is broken by the quantum theory is called an anomaly. And there are two types of anomalies. Either I break a global symmetry, or I break a local symmetry. Right. So we talked a little bit about local and global symmetries here. And we'll talk a little bit more about it in the next lecture. But either I break a local symmetry or I break a global symmetry. Now, one of the things about symmetries is that they're kind of sacrosanct in the theory. So if a process is forbidden by some symmetry, that's forbidden. Okay. But if you can break that symmetry, now suddenly something that was forbidden is now possible. Okay. For example, there are a couple of anomalies that are famous. Right? One of them is the chiral anomaly. Okay. So certainly particle decay cannot take place classically. And it cannot take place classically because chiral symmetry is a classical symmetry. Right? So whatever happens has to obey that symmetry. Okay. So so certain particle decays cannot take place classically because they are forbidden by the symmetry. But then you quantize the theory and you get a chiral anomaly. Okay. And the chiral anomaly suddenly allows these particle decays to take place. So these are actual physical things that are taking place. So global symmetries, global anomalies are sometimes good for the theory. It's certainly not bad. You can take care of it. When you break a local symmetry, the resulting quantum field theory is sick. Right? It's an inconsistent theory. We're going to talk a little bit about this a little later, but local anomalies are bad. If you can't cancel a local anomaly, then throw your theory away. Okay. All right, so let me stop here. Pick it up again.